Good afternoon, everybody. My name's Dan Rogers. I'm a curator of archaeology in the anthropology department. For about the last 15 years, I've been working on various kinds of computational models, especially what are called agent-based models. In ecology, they're often referred to as individual-based models. This afternoon, I want to give you two examples. Primarily going to talk about climate change-related issues with both of those. The first model is based in Inner-Asia, and this is the area that I do archaeological and historical research in. We have a number of test landscapes that we work with there, and our models use a Mason simulation system, and they're coded in Java. I like to compare different landscapes. The results are remarkably different, not only in terms of adaptation of the landscape, but the social organization as well. Aigangol on the left and Baga Gazarin Chulu on the right. To put a finer point on it, here's the average biomass density, BGCs at the very bottom there. If we crank up our agents and we let them go on the landscape, they have a pretty sophisticated social system. They remember their ancestors, they know their friends, they like to camp with their friends, they move their herds around in search of better grass. They live and they die, they give birth to new children, the children get married and have new households, the parents give dowries, in times of trouble, socially related groups share resources. If we take this kind of total world, this simulated total world that we've created on real landscapes, we can look at a variety of things, and I'm kind of interested in these abstract concepts of phase transitions, or basically abrupt changes, and how we might understand that in terms of climate change. For the pastoralists in Inner-Asia, one of the critical issues is extreme weather. That kills the herds very rapidly if you have a late spring snowstorm, and there have been modern examples of that. So we can look at the anatomy of some of these events. The word Zud is Mongolian for snowstorm. And we can look at the emergence of new steady states, the relationship between the scale of the external forcer and the actual impact, which is not a very clear relationship at all. But because we have this calibrated pretty well, we can really dig deep into looking at the anatomy of these kinds of events. We're also working on a second model, or another model rather. This is our current NSF-funded project, and it's primarily focused on the Arctic and boreal regions of the entire planet. But right now we're working primarily on Canada as our test case. We have about 16 million agents in Canada. One thing that we do is we compare the Canadian demographic data and climate change data to two popular CO2 emission scenarios, the optimistic one on the left and the pessimistic one on the right. So hot off the presses, or maybe I should say cold off the presses, we have some simulation results. One potentially disturbing pattern we're seeing, or not expected pattern, is that the optimistic and pessimistic trends are tracking almost identically. Now, intuitively, we wouldn't expect that to be the case. Note that this graph only takes us out to about 2020, and as those scenarios go through the course of the rest of the century, they diverge a little bit more. However, this is something that we need to double check with our calibration, and we're still trying to figure it out. We think that the model works correctly, because if we introduce a crazy high temperature increase like 1 degree a year, we get that red line at the top, so that we know that infrastructure expenditures do in fact go up if the temperature goes up. So this is in response primarily to the necessary repairs to infrastructure related to permafrost melt, which is occurring primarily in the northern parts of Canada and really actually affects relatively few people. That's it for today. Thank you. Right, all the models have parameters, sets of parameters. Every parameter has to be thoroughly validated against empirical data. Sometimes, because these models are, in essence, an elaborate hypothesis in themselves, there isn't always empirical data, or it isn't always possible to actually obtain it. So sometimes it's based on theory, or it's based on our best interpretation of what we have. So we use a lot of ethnographic data. One of the things we're calibrating with is Dust Bowl era changes in Canada. We had a period of about 10 years where the temperature was up, the droughts were increased. There was also a global economic crisis at the time. But it was interesting for us to see how much money Canada, even in the 1920s, spent to remediate this problem and literally move people to the north to clear new forest. My name's Dan Rogers. Since grade school, I've been fascinated by archaeology. And I've been in the museum for quite a while. And I probably have done, actually I counted it up the other day, 27 archaeological field seasons. And lots of excavating, lots of travel in Latin America and the Caribbean and East Asia. But then I also, in recent years, I've also thought more about how we utilize all the data that we come up with. And I became fascinated with the interdisciplinarity that these agent-based models seem to bring out. And I started working with a group at George Mason University, which is very interdisciplinary. It's kind of hovers around the social sciences primarily, but everything from political science to mathematical sociology. And that kind of interdisciplinarity also has a parallel, I think, with how we might in the very near future need to really approach some of the thorniest challenges that the planet faces. And I guess I would refer to this as kind of a total science approach, so that ecology and biodiversity and the social sciences, as well as other disciplinary perspectives, are brought together to address things such as climate change, that's one I work on, but also poverty or violence or any number of other challenges that the planet faces. And I think this is the wave of the future, and I'm really excited to be part of trying to figure that out, and it's been a lot of fun.